Here is a quick overview on how to find the work done during an isothermal compression of an ideal gas. Start by clicking on the gas itself to compress it. You'll notice that as you are doing work to the piston, heat is escaping at the same rate. This will keep the internal energy and the temperature of the gas constant. Once the compression is done, we can start working on our problem. Okay, so I took a screenshot, and what I would suggest doing is recording the number of moles. In this case, it's 263. I would then list the initial and final conditions of the gas. The initial would be your starting point. You want to write down your pressure, your volume, and calculate your temperature. The final condition is at the end. Again, you want to write down your pressure, your volume, and calculate your temperature. Okay, so you're going to have to estimate as best you can. So it looks like our pressure is maybe 195 kPa. It looks like our volume is a little more than 3.1. And that's meters cubed. Our final number for pressure seems to be around 360 kPa with a volume of about 1.58 meters cubed. You're now going to use the ideal gas law twice. Once for your starting condition and once for your final condition. Make sure when you do your pressure, you put it in pascals. Volume, you can leave in meters cubed. Moles. Ideal gas constant. Solve for temperature. You should get the same temperature at the beginning and at the end, but do it twice. Solve for temperature both times. And if they do not come up to be close to the same number, you know you did something wrong, or maybe you just misestimated either your pressures or volumes. Once you have all this done, then you're going to do work. Work equals P delta V. Okay, the problem is the pressure is constantly changing. So we're going to have to use little bits of work that are done when we move little bits of volume. Okay, we're then going to integrate both sides. We can then get work. We can pull out the negative sign. We can integrate from volume 1 to volume 2, our initial and final volumes. The problem is we need to write P as a function of V. So we're going to use the ideal gas equation. We're going to solve it for P. And then we're going to plug that in. Okay, we could then pull out of our integral the number of moles, the ideal gas constant, and the temperature. They're all going to be constants. Then hopefully we get something that is familiar to you from calculus, and we can integrate 1 over V dV, and that will give us the natural log of volume from V1 to V2. You now plug in all of your values, including your starting and ending volumes, and you find your work. It's going to be a really big number. You want to divide it by 1,000 to get it into kilojoules before you enter it into your program. Hopefully we did enough detail that you can work out the rest.